Okay, so thank you for joining me on here. As I apologize for the late notice, but that was all the notice that I had, that public schools are closing at 1:15, which means my daycare is closing at 1:15, which means I had to run home so that my husband could pick him up and that I could hold class. So I was really hoping to see all of you in person, but it was not to be. So for those of you who are still on campus, you may want to leave early as well. Apparently we're supposed to have lots of ice or something. I don't know. It's every week is a new fun thing here. So let's see. I sent out an email on Friday letting you know that homework 2 is now available. First off here, we're going to finish this handout that will allow you to complete it. It's a short homework. It should be pretty easy to do. Please let me know if you do run into any problems or if you have any questions on that. Does anyone have any questions yet? Is that a no? Hello?
No question from me.
No questions. Anyone else? All right, can you all hear me?
Yeah.
Okay, but you're no questions. All right, that's all I need. I can't see you shake your heads. So we'll have to go the audio way here. Okay then. Homework 1 I had hoped to have back to you before class, but again my morning got interrupted, so I will send those back hopefully later today. If there is anything that is incorrect on homework 1 or something that I want you to change, I will ask you to do so. There's a due date for the revision a couple weeks from now. That way you can make sure that you have a correct version of it for your records. If there are there any other issues we need to discuss before we dive in? Anybody? All right, then let's start back to where we were at the end of class last time. We were just starting this example 2A. Everybody see that in front of them?
Yep.
Yep, okay. So we have then, this is just a general linear model example. The idea is to reacquaint you with the process of interpreting slopes, as well as tests of univariate significance, as well as multivariate significance, which is the new part that the syntax in terms of asking for it that you may not be familiar with yet. So this example comes from chapter 2 of my book, and we are working with a fictitious data set of 550 older adults. We have predictors, or covariates, if you want to call them that. To me, those words mean the same thing, of age and grip strength being a proxy for physical function. Because those are continuous predictors that do not include 0 as part of their natural scale, I am opting to center those, and so this code right here creates new reference points for those predictors of 85 years and 9 pounds of grip strength. Both of those were near the mean of the sample, so that's why I picked those. There's already another variable in the data set keeping track of men and women. So that variable is called sex MW. Again, my notation here is to keep the centering constants at the end of the name so I can remember who the reference group is. So the sex MW to me means men versus women. So men are the lower category, women are the higher category of 0 and 1. And then I also have a contrast for dementia group where we have none as the reference group. So none versus future, and then none versus current as the two contrasts that we need to keep track of the 3 groups that we have here. And I ran some descriptive statistics. If you run things in SAS, this is the type of output that you're going to see. It defaults to HTML output, which looks like this in the HTML blue style. However, in my handouts, I use the old school text output because it's easier to annotate and to paste in. And so that's what you'll see for the rest of these. So I think we did this model on page 2 last time. Does that sound right?
Yeah, that sounds right to me.
Good. So empty model, more specifically, empty model for the means, meaning no predictors whatsoever. This is not something you would normally do when you're running any kind of general linear model, any type of regression or ANOVA, but it is the very first step that when you're doing any kind of multi-level analysis, so for longitudinal data in our class or cluster data in other contexts, the goal is to figure out exactly how much variance there is to be predicted in the outcome. So we have the cognition outcome that we're analyzing here. Cognition per individual. So this is a cross-sectional example, just getting started with acquainted with proc mixed. The model has a residual for each person, and the only thing in the model is this beta 0, which is the fixed intercept, meaning everybody gets the same value for the intercept. And if you know nothing else about a person, the fixed intercept is the grand mean as your best guess for what their outcome should be. So that's what this model is going to return to you, the grand mean given by beta 0, and then E for each person will have a variance across people known as the residual variance in traditional parlance. So in the output, you get, among other things, those two parameters. So under this table called covariance parameter estimates, there is a term called residual. The estimate for the residual is referring to its variance. So everything in this table right here in the future is going to be either a variance or a covariance or a correlation. They all are going to deal with parameters for the model for the variance. In this case, all we have is E. All we have is a single type of variance for differences across people. And because we have no predictors, this variance estimate of 120 is all the variance in cognition to be accounted for. You will see, along with the estimate, a standard error for the variance. The estimate divided by the standard error is this column right here, Z, and then there's going to be a p-value that goes with that Z. Now I am here to tell you that these two numbers right here in covariance parms, you are never, ever, ever allowed to report or use. Now, why might this be? Well, what is the smallest number that a variance could possibly be? 0. And this Z value is testing a null hypothesis of 0. So if a variance were to have a usual two-sided sampling distribution, that would mean that sometimes it would be negative and sometimes it would be positive, but that can't happen. So the idea of using what is known as a traditional univariate wall test, that's what this is right here that I've highlighted, this Z value, entailing a two-sided sampling distribution, that can't possibly be correct. And the closer to 0 the variance is, the more incorrect it's going to get, because in reality the test is at a boundary on one of the sides. So when we have questions about whether or not a certain type of variability is significant, we're going to do something else to answer them, and that something else is what's known as a likelihood ratio test. We will get to that later today, possibly Thursday. The information for that test is contained in this next table, which we can ignore for right now. It is repeated with more detail in the table after that. And then last but not least, solution for fixed effects is the thing that we're interested in if we want to know what happened with our model for the means. And right now, there's only one parameter, the fixed intercept, which is 24. So that's the grand mean of my outcome. The variance around that is given up here as the 120. So two parameters in the model up to this point. Okay, questions so far? Okay, so this covers section 1 of your homework, being able to recreate this on your example data.
I got one question.
Sure.
So for the covariance residual, we cannot trust the p-value, but we can trust the point estimates. That's
yes.
Correct?
Yes. You also cannot trust the confidence interval that would be formed by two standard errors on either side for the same reason.
Okay, gotcha.
Variances tend to be skewed since they can't go lower than 0. So that's why we're basically going, you can report the estimate and you can report the standard error, but then after that, nobody really should do anything with this Z and this P. So this Z and P, this combination of testing the single estimate, is what's known as a univariate wald test. Likewise, down here in the model for the means, I have a column that is T and P. Do you remember from last time what the difference is, why one is called Z and one is called T? I'll give you a hint. There's an extra column down here in the solution for fixed effects that's not up here. Don't be shy, come on. Hello?
The t-test is for like limited sample size. Z is like approximation to infinite
Yes,
sample size.
exactly. So even though estimate divided by standard error is this column right here in both cases, what that ratio is treated like depends on whether or not denominator degrees of freedom are being used. And down here they are. So that's why this is called a T, where the numerator degrees of freedom is 1, and the denominator degrees of freedom is this 549. And that comes from the number of people, which is 550, minus one parameter that is being estimated, which is this intercept. So unlike the Z value up here for the variance, we will typically pay attention to the p-value for the t, because the null hypothesis of 0 typically makes sense when you're testing slopes. Now in this case, we're saying that this intercept estimate of 24 is significant, but do we care about that? What do you think?
I'm gonna say no.
No, I would say no too. Why would you say no?
With the intercept, I guess it would depend on exactly what we're measuring, whether 0 is a meaningful number. Since we're just testing whether or not its cognition is greater than 0 at the intercept, it doesn't seem to be, I guess, a useful interpretable statistic.
Yes, agreed 100%. In this case, this p-value tells us that the mean of 24 is not 0. That is not terribly helpful to me. An example of when it would be helpful is, let's say that on my scale, 0 had some sort of reference value, such as normal functioning in the case of whether or not we're trying to diagnose someone with some kind of cognitive impairment. If the mean for the sample was significantly different than my reference value, that might tell me something about the sample that's of interest. But in this case, the fact that it's not 0 is just what it is. It's not terribly informative. That typically won't be the case for slopes, but it is usually the case for intercepts. Okay. So let's put some stuff in the model. Top of page 3. Here's my new model. So I have added 3 fixed effects. Beta 1 is going to be the slope for continuous age. And note that I have used the equation to show the centering value. So age minus 85 conveys that 85 is my new 0 point. Likewise, beta 2 for grip minus 9 conveys that 9 pounds per square inch is my reference point for grip. And beta 3 is for the dummy code that differentiates men from women. And note that age, grip, and sex all have a subscript of I because they vary across individuals. Each person has one value. E now, the same model for the variance as before, but we would expect the variance across E's to be reduced to the extent that cognition is predicted by age, grip strength, and gender. So then when we go down to the proc mixed syntax to make this happen, you'll note that the 3 fixed effects are added here. So the model statement looks a lot like the equation. The only difference is that beta 0, the fixed intercept, is included by default, so you don't have to write it. But otherwise, you are writing out what fixed effects you want to have in the model. And so right now, because these are all listed separately, we are asking for their main effects in the model. After the slash is where you ask for specific model options. The first one is going to provide chi-square test statistics in addition to F's. The solution line actually gives us the solution for the fixed effects. For whatever reason, the answers, the point of the model, is not a default piece of output. And this last piece is going to come into play later. It stands for denominator degrees of freedom. When you're doing multi-level modelings, there are choices for this. Right now, there really isn't a choice. This BW stands for between, within, and it just is the traditional general linear model approach with respect to denominator degrees of freedom. This contrast statement we talked about last time. This is the idea of duplicating what in a regression program would come out by default, which is the model test of whether the R-square is significantly greater than 0. So this is an example of what's known as a multivariate wald test, where it's a wald test with 3 degrees of freedom, numerator degrees of freedom. I am testing the combined effect of age, grip strength, and gender, whether together they account for significant variability in cognition. And this chi-square option again converts the F that this test gives us into the equivalent for a chi-square. Okay, with me so far?
Yes.
Okay, cool. So I'm going to go straight down to the interesting part here, the solution for fixed effects. And so these estimates, I will point out, are unstandardized. They're in the units of the original variables. In regression, typically people pay attention more to standardized estimates than unstandardized because they can be effect sizes that are bounded from 0 to 1. There is no such thing as standardized effects in multi-level modeling. There's not an agreed upon way to standardize that applies to every case. So from the rest of the semester, we are dealing only with unstandardized coefficients. And so I want you to get used to seeing them and knowing what to do with them. So our model now has 4 fixed effects, 4 parameters in the model for the means. And this out here, this last column where it says is B0, is B1, this is me being nice, by the way. This is not something that comes out in SAS output. I will typically try to annotate things for you that the first time you see them. My previous students sometimes called this Proc Lisa. See, it's supposed to be a joke. But yeah, I once had that question of whether, like, what's the option that gives you the interpretation? Like, wouldn't that be awesome? But no. That is why I have a job, because that option is not readily provided. So let's go through these here. This should be something that you already know how to do, but I just want to make sure. So previously, in the empty model, our intercept was 24. Now it is 26. Why is it different?
Put in more parameters.
Put in more parameters. So 24 was the grand mean. Now what is 26?
It's 26 is the predicted cognition given the person is 85 years old and their grip strength is 9 pounds and that their sex is male.
That's it. So the difference is that this is still a grand mean of sorts, but it's not a grand mean, it's a conditional mean. You can think of it as a mean in the sense that anyone in the data set who shares those same characteristics, age 85, grip 9, and is a man, they all get the same 26.9 as their intercept. So when you think model for the means, it is still a mean in the sense that it's an aggregate across people who share the same characteristics. So you can think of this as the fixed intercept. You can think of this as a conditional outcome, an expected outcome. You can also think of this as the "you are here" sign in the map of our data. So that's our reference point. From there, we talk about what happens to that reference for different kinds of people. So what happens according to this next coefficient, this minus 0.4? Should I start calling on people? I'm going to call on people. Ori, your turn.
I'm sorry.
My question is, put this minus 0.4 in a sentence for me, please. And you're allowed to phone a friend for help if you want. You can call on someone else instead if you'd like.
Sorry, the interpretation of the estimate?
Yep.
Oh, okay. So for an increase in, I'm sorry, it's like the effect is decrease.
That's
increase in H85.
Yeah, so cognition is our outcome. So what happens to our outcome according to this coefficient?
Okay, the cognition decreased by 0.4338.
Per.
Everything 0.
Holding everything else constant, cognition decreases by 0.4338 per, or for every. What's the unit here that's attached to the 0.4?
Wait, so the H85.
So these are older adults, and age is measured in years.
So for every increase in year?
Yep, so if I'm 85, my intercept is 26.9. If I'm 86, it is lower by 0.4. So that's one thing that I found students sometimes forget when they're writing up results sections, is that the coefficient is always tied to per unit x. But per unit x is the generic term. You have to go into the variable and think, okay, what's a unit? So in this case, for every year older, the cognition outcome is expected to be lower by 0.4. So yes, I think we got it. And given the p-value that goes with that, we can say significantly lower. You will find that I pay little attention to the p-values because I want you to learn how to interpret the coefficients no matter what, but just to keep that in mind. Grip, who wants to try grip strength? And here it's pounds per square inch. That's what these units are. See, this is where I really wish I could see your faces, because there's two possibilities here why no one is answering me. Number one is you're shy and you don't want to talk. Number two is you don't know the answer.
When holding others or constant, effect like 0.5 or 0 increase in variables unit per you expect 0.546 increase in cognition per unit increase in grade.
There you go. Yes, exactly. So you do know it. You're just shy. See, that's good, because I would attempt to solve the problem in very different ways depending on what the answer was. So shy is okay. So yes, exactly. For every additional pound of grip strength, cognition is expected to be higher by 0.5. Just a note on language. Sometimes people say increase or decrease. I tend to reserve those words for effects that are longitudinal or within persons. Because this is a cross-sectional example, people aren't changing per se. We're talking about differences between people. I would say that, cognition is higher in stronger people, or cognition is lower in older people, but I wouldn't say increase or decrease. So it may be a semantic distinction, but it's one that I think helps clarify the setting of the study. And good, last but not least, -3 here. Someone want to try that one? Let's see, who can I call on now? James, I'm calling on you.
Yeah. So with this estimate, if you're a female, since it's a categorical predictor, we now expect, holding everything else constant, for your cognition to be 3.7988 units lower.
There you go. Women are significantly lower than men.
Sorry.
Yeah, go ahead.
Was that a question? Sorry.
Nope, that was a statement. Women are significantly lower than men.
Yep.
In this sample. I never try to generalize to any kind of population. I'm just talking about the sample.
In the sample.
Yep, that's what I would say. So, okay, good. So then so this output tells us per predictor whether each is uniquely significant, holding all the others constant. So that language that you learned in regression is still going to apply to everything that we do. Then whether or not this model together is any good, whether these effects together account for significant variance, that question is answered down here with this model f-test. So this is the result of our contrast request up above. So you'll note that in the contrast statement, I have commas separating each of the effects. So what I'm asking for in typing the names of these predictors is actually a reference to their beta weights. So I'm saying test beta 1, beta 2, and beta 3 all at the same time. That output then has 3 degrees of freedom because I'm testing 3 fixed slopes. It has denominator degrees of freedom of number of people minus number of fixed effects in the model, which is the 3 slopes plus the intercept. And that forms an F of 20. F times numerator degrees of freedom is chi-square. So whether you report chi-square or F is really immaterial. The difference boils down to whether or not you're going to worry about denominator degrees of freedom, and in this case it's so high that this doesn't make a difference. So yes, this is the test of our model R-square. That's what we just asked for. So now the R-square itself. Do you see anything in this output that I've given you that gives us the R-square directly? Nope. And that's because in the world of longitudinal models and multi-level models, there is not a single agreed upon R-square. In simple versions of models such as the general linear model, in which you have only one kind of error variance, R-square is defined. But it doesn't show in this output because it isn't always the case that we can do that. But conceptually, what we want to do is look at how much variance was there to begin with. So from the empty model on the previous page, the variance in cognition was this 120. Now it's down to 109. So there's a formula to figure out what the change is in this and to figure out what the proportion is. And in this case, you can either do the math yourself in Excel or on a calculator. And the formula for it is what it was minus what it is over what it was. Meaning what it was, 120, minus what it is, 109, divided by what it was, 120. I wrote a little program that does this for you using saved pieces of output in SAS. So here is the formula that I just gave you. What it was minus what it is over what it was. That's going to generalize to more complex models that have multiple types of variance. This type of formula for an R-square will give us a variance type specific estimate of variance accounted for. It's 9%. And we know, based on this contrast up here, this multivariate wald test, that 9% is significantly greater than 0 because that's what this f value, or alternatively, f times 3 gives us chi-square, tells us that. So I've asked you to calculate R-squares and significance tests for R-squares in your homework 2. To make those calculations more streamlined, I wanted to point out the use of the little program. So in the example file that goes with this example, the SAS files here, let me open that up real quick. I have SAS installed on my laptop here, so I don't have to log into the virtual machine. I have this little program right here. So this says model R-squared macro. To be able to use it, all you have to do is copy and paste this text and run it. You don't have to change anything. This is just a program that takes saved data sets and does the math for you to figure out what the R-square is. To tell it which information to pull from to be able to do this, that's where this line comes into play in each of my examples. So the statement ODS output. ODS stands for Output Delivery System. Output means save it to a SAS dataset. So what it's doing is taking this table right here, which it thinks is called COVPARMS in SAS parlance. It's going to save this table where the headers in the output are the column labels, and this is the information per row. It's going to save this as a data set called COVEmpty. That's the name that I created. Then for the next model, I asked for it to do the same thing, except that I called it COVAGE meaning the model that has all this stuff in it. And then down here, I fed those two data sets in as arguments to a function that it then does for the math for you. So this is just me trying to help you not have to type things into Excel or get out your calculators. If this is confusing, you don't have to use it. But the arguments then is the baseline model, the model with fewer parameters, and a model with more parameters. That allows you to calculate R-square changes across 3 different models if you want to. Up to this point, there's only 2 models of interest, and so that's why I have COVEmpty in both places. When you run the program, and you can run this in SAS and see what happens yourself using my examples, you get this piece of output. So it compares the variances estimated for each model and then calculates the proportion reduction. So then putting it all together, these 3 fixed effects, each are individually significant. Together, they account for significant reduction in variance and in cognition, and the amount of that reduction is 9%. Okay, how are we doing? Good. Okay.
I had a more I guess general question about the order of parameters. Does it make a difference in their estimation? I want to say no, but I guess there's just a sentence in chapter 2 that I read that made it sound when we're moving from, say, just one parameter model that includes, or a 2 parameter model that includes the intercept and or I guess 3 parameters. If it includes intercepts, the unexplained variance, and the say aid, and then if we add grip strength on top of that, then it was shown that those 2 variables were correlated with each other. So I was curious on where their shared variance goes, and does that matter on order of the parameters, or is it kind of shared between? Is the shared variance between the 2 kind of given to both the variables in some way that is that's a little bit unpredictable? Or
great question. So let me try to pull that apart. So one thing I think I heard you ask is, within the same model, does it matter like which you put first?
Yeah.
Okay. So long as you are looking at type 3 sums of squares, the answer is no. That is going to be the case like 99% of the time. There is an option for something that's called type 1, which parses the variance accounted for hierarchically. That is useful in certain circumstances in which there's a natural order to the predictors that you want to maintain that order. I can only think of one instance in my whole life where I thought that was a useful thing. So for all intents and purposes, no. Once they're all in the same model, it doesn't matter what you list first. So I think you were talking about the situation in which, let's say, so you have age, right? And then you add some more stuff. So the effective age that you get all by itself is not going to be the same effect as it is in the context of other predictors whenever age is related to those other predictors. As you said, there's sort of a common variance that none of them gets credit for. And where that shows up is in what is known as the asymptotic covariance matrix for the parameter estimates, which is a piece of output that I didn't print because we rarely need to refer to it. But in the solution for fixed effects right here, each of these has a standard error. You can think of this as a standard deviation around this parameter estimate as a mean. So the standard error squared is the variance of this parameter estimate, and in reality there's a matrix that has all four of these things in it, so it's a 4x4, where the diagonal of the matrix is each of these standard errors squared, but then there's also an off diagonal, which is a covariance between the standard errors. And that is where that sort of the fact that they fight against each other, that common variance, shows up. And so this multivariate test, what it's doing behind the scenes is factoring in not only the standard error for each one of these, but the covariance between them to get a test of the set as a whole. It is technically possible to fit a model where each of these things by itself is non-significant, yet together they account for a significant R-square, because each of them does not get credit for the joint contribution, but the model as a whole still gets credit for the joint contribution.
Okay.
Does that help?
Yeah, so that means the interpretation of the estimates are the variance explained
uniquely
by that particular predictor.
Uniquely. The key word is uniquely. So when I run these types of models, what I tend to do is to run each predictor that I'm potentially interested in separately first in its own model, and just see if bivariately, like if the predictor is related at all. Then I would combine predictors across multiple models in whatever order made sense for my research questions. So for instance, in this, the field that this example is based on is cognitive aging, where, of course cognition is going to be related to age. The question is what else matters? So in this field, age is just a variable that you control for no matter what. It's expected, and people will yell at you if you don't put it in. Every field has a variable like that. So because of that, age goes in first, and then the onus is on me to show what is the unique effect of these other predictors after controlling for age. So if we found out, let's say, that grip strength was not significant, I don't know just from looking at this output whether grip strength just doesn't matter at all, or it doesn't matter only after controlling for age. If I started with a model that I just had grip strength by itself, and it was related significantly, and then I went to this combined model and the significance dropped off, I would know that the story is not that grip strength doesn't matter, it's that grip strength doesn't matter uniquely.
Okay.
So unique is the key word when you're interpreting models with multiple predictors, and I think it's an important part of the story because people would argue with each other about what else should be in the model in order to make that unique claim be scientifically noteworthy.
Okay, thank you.
Sure. A long answer to a short question, but does anyone have other questions? Okay, so that's why it can be useful to look at these individual coefficients, but it can also be useful to look at these multivariate coefficients for the set of things. So I want you to be able to do that. And note that in this case, because I listed all 3 coefficients, this f-test that's reported down here is the test of the model R-square. If I wanted to do something like, let's say that I took age out of it, and I asked for something like this, could I do that? Sure, nothing's stopping me. It would be 2 degrees of freedom if I did this without age, and it would be testing the unique contribution of these 2 things after age. That would be otherwise known as a test for the change in R-square in a sequential type of regression model. So if I put age in as a first step, and then the next step had grip strength and gender, then that test of change in R-square, that's what this contrast would give me. So these contrasts are agnostic as to what you put in them. You can put anything you want, and depending on the constellation of your command, you can either ask for the whole model or a subset of the model to answer whatever question you have. Okay. So, with me so far? Yes, thank you. I'm going to hope everyone is nodding. So let's see what happens then when we put a grouping variable in. So I will show you all the ways in which you can either do this yourself or let the program do it for you. And I just want you to know what you're asking for and therefore what the output means. So we're adding in, this is the top of page 4 here. This is equation 2.8 in chapter 2. We are adding in the effect of dementia group. So dementia group is a 3-category variable for there's no dementia in the person, they are going to be diagnosed in the future, or they've already been diagnosed currently. So there's 3 types of people here. By far, the most prevalent, you can come back to the descriptive statistics here on the first page, 73% of the cases are no dementia. 19 or 20% is going to have dementia at some point during the study, and 7% means they already do. So I want you to pay attention and note these differences in frequency, because the differences in size means that some of these comparisons are going to have a lot more power than the others. In particular, a comparison of 2 versus 3 is going to be relatively underpowered relative to a comparison of 1 versus either of the other 2, since 1 has so many more people. So let's take a look then at what would happen if I made the dummy codes myself. And this is what you traditionally have to do in regression software. So software that is designed to have only continuous predictors in it, you have to trick the program into treating categorical predictors as continuous by making your own codes. So this dem_nf variable and this dem_nc variable, these are both a value of 0 if the person is none, the reference group. NF takes a value of 1 if it's the second group, and NC takes a value of 1 if it's the third. So then to get down to what the model says the group means would be for any type of person, beta 0, the intercept, is for the reference type of person. Beta 0 plus beta 4 gets us to what the model says the mean would be for a future dementia type person, and beta 0 plus beta 5 gets us to what it would be for a current person. So then if we wanted to figure out how the model tells us about the 3 possible group differences, that's down here. 2 of them are already given to us. Future versus none is given to us as beta 4, current versus none is beta 5. The missing one, we could look at these means and calculate by hand what the difference is, but we wouldn't get the standard error for it. To get the standard error for it, we have to ask for it. And if we know what the model says the mean should be for future, and we know what the model says it should be for current, then it's the difference of those 2 coefficients. So it's beta 5 minus beta 4, or equivalently, minus 1 times beta 4 plus beta 5. And so if you come down here in the code for this new model, this is a lot of code and a lot of notes because I want to make sure that this is as clear as possible. You'll see that we have 2 new fixed effects written in after on our model statement here. I have two examples of multivariate wald tests. The first one here with degrees of freedom 5 lists everything that's in the model. So that's the same thing as asking for whether the R-square for the model is significant. I have also written a statement that tests only a subset of the fixed effects, and this time it's listing the two new ones. So you can think of this second statement as doing two different but equivalent things. One is that this is equivalent to the traditional omnibus main effect of a categorical predictor. So it's a 2-degree of freedom test of whether dementia group matters at all. Or because these two parameters were the next two things added relative to the previous model, you can also think of this as the test for the significance for the change in R-square. Either way, it's the same idea. Then to get down to the group means and the group differences, I have estimate statements that we also looked at last week as well. So just to review, anytime you're asking for an intercept or an expected outcome or a conditional outcome, a conditional mean, an adjusted mean, all of those words mean the same thing. You have to start with beta 0. So this intercept 1 means I need at least one beta 0. To get to what the expected mean would be for the none group, I don't need any beta 4s and I don't need any beta 5s because the none group is the reference. To get to what the intercept would be for the future group, I need one beta 4 and no beta 5s. And then last, to get to what it is for the current group, I need no beta 4s but one beta 5. And so then if I want to know what the differences are, I can literally take these statements and subtract them. So if I have none versus future, if I put future first and subtract none, the two intercepts drop out. I end up with 1 NF and 0 NCs, and that's the same thing as beta 4. Likewise, this one gives us beta 5, so these two are not strictly necessary, but they're here for pedagogical purposes. The one that we don't get by default, the third contrast that is model implied, is the one that's right here. And this is beta 5 minus beta 4, written as minus 1 times beta 4 plus 1 beta 5. So that's the missing one that we would not get unless we change the reference group. All right, and note here that these are conditional means. Not only are they group specific, but they also are adjusted for the other covariates. So this would be thought of as an ANCOVA type model, because we're looking at group differences after controlling for age, grip strength, and gender. Because age, grip strength, and gender are not mentioned anywhere in these statements, they are implicitly held to their 0 values, which means age 85, grip 9, and men. So because there's no interactions in the model, these dementia group differences are irrespective of any of those covariates. The same group differences would apply. Another way of saying that, hint, hint, homework question, is that these main effects are all marginal. So when I look at the output here, this is the coefficient for age for everybody. This is the coefficient for grip for everybody. This is the gender difference for everybody. It is only when these variables are part of an interaction that we would say this is the effect of age specifically for men, or specifically for women, or specifically for people without dementia, something like that. So you will have questions in your homework asking you about whether this is a simple main effect, meaning specifically for a certain type of person, or a marginal main effect, meaning marginal for everybody. If a predictor only has a main effect, it's marginal. It's for everybody. Okay, how are we doing?
Good.
Good. Okay. Questions? All right, so let's look at the output then. The intercept here has shifted further. It used to be 26 and now it's 29, because now it is not only for an 85-year-old with 9 pounds of grip strength who's a man, but it's also for a person who is never going to have dementia, at least as far as the data were collected. Likewise, the effects of age, grip strength, and gender are all interpreted similarly, but numerically they have shifted. So they're a little different than they were before because these are now the effects of each of these predictors after controlling for dementia. So to the extent that people who are older are more likely to have dementia, or women are more likely to have dementia, these predictors would have different effects. So unique, again, is the key word. The new pieces, though, is what I wanted to highlight here, the effect of the grouping variable, where none is the reference group. And so these two effects then correspond to beta 4 and beta 5. Relative to the none group, people who are in the future group are 5 points lower, significantly so. People who are in the current group are 16 points lower. So here's a news flash. Dementia is not so good for you. No one saw that coming, right? Especially for your cognition. So each of these coefficients is significant, meaning that the difference between the none and future is significant, and the difference between none and current is significant. Now, if we can figure out what the missing contrast would be just from looking at these numbers. So the one that we didn't get is F versus C. It looks like there's about an 11-point difference there, give or take. The question is that difference significant? And we don't know the answer to that without knowing its standard error. Now, I could give you the formulas to compute the standard error of the difference, but it's a pain in the ass and I don't want you to spend your time doing it. I want you to learn how to make the software do it. So this brings us to the very last statement that we wrote here, the estimate. That's the missing contrast. So here's the results of all of those statements. First off are the conditional intercepts for each group. So again, these are the group-specific means at the zero values of the covariates in the model, because that's what we asked for. These are the mean differences between the groups, and these mean differences are irrespective of the covariates, meaning -5 is the difference between none and future for anybody. -16 is the difference between none and current for anybody. And here's my eyeballed -11 as the difference between the future and current, and there's the standard error for it. So note these differences, but note the standard errors. Do you see a pattern here? All things being equal, higher estimates would have higher standard errors if they're measured on the same scale, but the standard error is 1.7 for an estimate of -11, whereas it's 1.5 for an estimate of 16. Any guesses as to why these are so different?
Because the future and the current group, they have few sample sizes, which adds to the uncertainty to the estimates.
Exactly. So even though the model assumes the same amount of residual variance for each group, the sample size is different, and that gives us greater uncertainty and lesser power. And so that's another reason why, even though if we know -5 is significant, we can guess that -11 would be significant, but we can't really know without knowing the uncertainty around it. So here then are the multivariate wald tests. The first one is listing all 5 fixed effects in the model, so that's the same thing as asking whether the R-square is significant. The next one is listing just the 2 new dementia effects, which is the same thing as change in R-square in this case, or more generally, the omnibus mean effect. And here is the result from comparing the variance accounted for across our models. So the empty model, we started at 120, went down to 109 after controlling for age, group, sex, and now we're down to 88. So we can say that we went from 9% variance accounted for up to 27% variance accounted for is where we currently are, which is an increment of 17%. So whether or not this 27% is significant is tested with this F of 41. Whether or not this increment of 17% is significant is tested with this F of 67. Okay. How are we doing? Good. Now, just as an aside, to follow up on something that I mentioned just a second ago, this model assumes, without testing, the same amount of variability within each of these groups. Now, that seems somewhat unreasonable given the process of dementia. So people without dementia may be relatively similar to each other, or at least more so than people with dementia. People with dementia may be a lot more variable based on how long they've had the disease and what type of dementia is and all that kind of stuff. One of the nice things about this software, these mixed algorithms, is that we can test whether or not there needs to be a difference in the variance across groups. That's actually one more line of code that would allow different residual variance estimates across each group, and we can test whether or not allowing those differences makes the model improve. So that's another extension of the traditional regression assumptions: normality, independence, constant variance. We can test for and include any evidence of non-constant variance via additional model parameters. So just keep that in the back of your mind as something else that you'll be able to do. So last but not least here, this is what it would look like if we let the program estimate the exact same model that we just finished, where it's treating dementia group as categorical by itself. So this is the same model. It has been what I would call reparameterized, meaning it's set up so that the reference group is different, but it ends up being the same model in that the same information is contained in it. So let me walk you through where the differences show up. Number one is we don't have our dummy codes in the model anymore. We have this variable called dem group. Dem group is the original 1, 2, 3 categorical indicator for which group is which. If I were to just put dem group in the model right here, it would try to draw a single slope through the 1, 2, 3, and that would be wrong and silly. Instead, I'm putting dem group up here on the class statement. So this is the same thing as a factor variable in R. It's the analog to I.dot in Stata or by in SPSS. It tells the program to make contrasts to give us a difference between every possible value. So when I tell it dem group, it reads the variable, figures out how many possible groups there are, and makes the contrasts that I need. The only difference between how this is going to be set up relative to what I did in the previous example is that it picks the highest group as the reference. So when I'm writing out the equation, I've changed the definition of beta 4 and beta 5 to match what SAS is doing behind the scenes, where current, which is number 3, is the reference. So I have a current versus none and a current versus future in here. The other way that it looks different if you let SAS do the coding for you, or if you let any program do the coding for you for that matter, is that every time you refer to dem group, you have to explicitly tell it which groups you're referring to, where there are spaces for integers for as many unique values as you have. So in this case, there's 3 numbers here because I have 3 groups. So if I want to test the effect of dem group as part of the model, because it's 3 groups, I need to list 2 of the pairwise comparisons. Doesn't matter which 2. It just corresponds to the idea that there's 2 degrees of freedom in testing across 3 groups. The other thing that's different when you allow the program to do the coding for you is that you have these extra statements available. LS means is your best friend when you are asking for group-specific means and differences. So in this case, it looks like I have an example here from the last time I taught this that needs to go away. I'll get rid of that. Sorry about that. That's what happens when I edit my slides and forget that I was doing that. LS means dem group means give me the group-specific means, all 3 of them. Diff equals all means give me all possible differences. And at then holds the group means at specific levels of the covariates. So note that I have 2 sentences here to show you what happens if you remember to put the add in versus if you don't. Okay, with me so far?
Yes.
Yes? Yeah, okay. So then down here, everywhere that there's dem group, there's going to be 3 numbers after it. So the omnibus main effect of dem group then is 2 different contrasts right here. The group specific means and the group specific differences, these 6 estimate statements and this contrast right here, all of this right here, all of that is given just by this line. My internet connection is unstable. Good to know. So when you use LS means, it's a very simple way, very quick way, I should say, to ask for group means and mean differences, and you can hold them at levels of covariates. When you put a variable on the class statement, it also then gives you multiple degree of freedom tests for its main effect, in addition to its univariate contrasts. So then down here, the output is going to look a little bit different. The solution for fixed effects is going to show the analog to the model equation up here, where it lists the specific contrasts that the model has created, that the software has created for you. So this dem group 1, 2, 3 then, it puts a 0 and dots next to the line that refers to its reference group. So if you're ever not sure who your reference group is, this is one way that you can tell yourself. So that means that the model intercept, last time it was 20 something, now it's down to 12 because it's changed the you are here sign. It's now the you are here sign for group 3 specifically. And relative to group 3, group 2 is 10 higher. Relative to group 3, group 1 is 16 higher. So it's the same information just with a different reference point. Down here is a piece of output that I only print when it contains unique information, and this is known as the type 3 tests of fixed effects. So there's that type 3 reference that I mentioned earlier in terms of that this is the unique contribution of each, and here this dem group is the combined test of these 2 contrasts, and so there's the F of 67 that we asked for ourselves via a contrast statement in the previous model. So it does that for you when you use LS means and the class statement. So that is there. And you'll note that the other ones is just a repeat of what's given up above, where F is the same thing as T squared. And here are the group means, and here are the group mean differences. So last but not least here, I want to point out what the least squares tables give you as a function of how you ask for the group means. So recall that in the code here, I had 2 different LS mean statements. The first one asks for dementia group means and differences held at specific values of covariates. The next one omitted that part. So the first 3 lines are with the covariates, and it shows you explicitly. This is the mean for group 1, holding age 85 at 0, group 9 at 0, men, sex at 0, and there's the mean. So this is what we got from the previous model. The next 3 lines then show you what happens if you forget to hold your covariates. It decides to put them at the means of the sample instead. Now there's nothing technically wrong with this, but it's weird. So let's say that you are trying to make like a bar chart or something like that to put on a poster. If you used these 3 means, for instance, they would be specific to somebody who is near 85, slightly stronger than our reference point for grip, but it's for somebody who is 60% woman and 40% man. Now, I'm not going to comment about how people view themselves and their gender, but in this particular study, they were not allowed the option for fractions. So in terms of coming up with model predicted estimates that correspond to actual people who are in your sample, this is weird. So this is where, when you're talking about trying to create predictions from your model, it's important to consider the levels of your covariates so that your predictions refer to realistic values. However, when it comes to testing those differences, it doesn't really matter, because dementia group is a main effect only, which means the group differences are irrespective of the values of the covariates. So they hold for everybody, they're marginal. So that's why the same group differences of 5, 16, and almost 11 hold in each of these two tables. So the point of this exercise is to preview all of the stuff that you're going to see this semester in more complicated models in a model that you should be able to understand. So you can either decide for categorical variables to do the coding yourself, and in which case you have to ask it for all the group comparisons of interest, or you can let it do it for you by using this class statement. Which is more convenient is really just situation specific, but I want you to be able to follow either type of example to use as makes sense for you. So, and then chapter 2 goes through a whole extended version of this that has interaction terms. I'm going to put that off for now so that we can head into longitudinal sooner rather than later, and then we'll pick up the interaction terms later in the semester when they're relevant. So, all right, questions?